And welcome to Linear Algebra, Chapter 5, Scalar Products and Orthogonality. Another name for scalar product is the inner product or the dot product. Is what we're used to calling it. But a dot product on Kn is just a special case of a general scalar product or inner product. And so chapter 5 starts with scalar products and then deals with orthogonality and orthogonal subspaces. So let's look in chapter 5, section 1, scalar products. As usual, we're going to let V be a vector space over scalar field K. A scalar product on V is a mapping, call it S, going from V cross V into K that associates any pair of vectors, VW, with a scalar in K. And it must satisfy three properties. The first one, SP1, is commutative. The scalar product of V and W equals the scalar product of W and V. The second one is distributive. If you have U, V, and W are three vectors in V, then the scalar product of U with V plus W is UV plus UW. And third, say if X is a scalar, then the scalar product of XU with V, you can factor out the X. Or if the X is on the coefficient of V, you can factor the X out of the first or second components. Now, there's a fourth property that not all scalar products have, and I call it SP4, and it's the property of non-degeneracy. The scalar product is said to be non-degenerate if, whenever V is a vector in V, and the inner product with V with any vector W in W being 0, then that means that V itself must be the 0 vector. In other words, SP4 says the 0 vector is the only vector in V whose scalar product with any other vector, including itself, is 0. So in other words, non-zero vectors don't always degenerate to 0 when you take their scalar product with other non-zero vectors. All right, example 1, suppose V equals Kn, our most comfortable space to look in. Then the usual dot product on Kn is a scalar product in the following sense of scalar products. So let's look at it, okay? So we're just going to briefly prove the three properties, SP1, 2, and 3, for Kn. Let x, y, and z be vectors in Kn, where they're represented by their components. Let C be a scalar in K. Then the dot product of x and y, by definition, is the summation of the products of the corresponding components. Xi times yi. I go from 1 to n. But the components commute. So xi yi is the same as yi times xi. So that easily shows that x dot y is the same as y dot x. And in similar fashion, you can see here that x dot product with y plus z is distributive, and you get x dot y plus x dot z. And third, clearly scalars can go in and out anywhere, and they factor out as needed. So that is clear to see. All right, so let's look at example 2. Very important example in calculus where we're defining a scalar product using a definite integral. A definite integral. Now, suppose our vector space V is the set C on the closed interval 0, 1. That means the set of all continuous functions on the closed interval 0, 1. So let f and g, and probably later h, be 3 functions in V, continuous functions on 0, 1, and define this mapping that associates f and g with the definite integral from 0 to 1 of f of t, g of t, dt. Now, the definite integral here can be taken over other intervals as well, but for the sake of simplicity, we normally, by standard convention, just go from 0 to 1. Show that this association is indeed a scalar product. So let f, g, and h be 3 continuous functions on 0, 1. Let c be a real number. And let's look at the definition. F with g is the integral 0 to 1 of f times g, but f and g commute. Fg is the same as g times f. So that means the integral of fg is the same as the integral of gf. And so we see that the scalar product of fg equals the scalar product of g with f. Similarly, we note that if you take the product of f with g plus h, that the integral f times g plus h, well, f distributes across the addition, and so you have the integral of fg plus fh, and then break that apart as the integral of fg plus the integral of fh. So that's the product of f and g plus the inner product of f and h. And third, we can see clearly that scalars go in and out as they may. The integral of a scalar times a function, you just factor out the scalar. So CF with G is C times inner product of F with G. I use the terminology scalar product and inner product interchangeably. We'll just note that our first 2 examples here, that is Kn and this example, also satisfy the property of non-degeneracy SP4, which you can prove. I'll let you play with that on your own. All right, now next, let's start with a vector space V over our scalar field K, and suppose it has a scalar product on it. Now, let S be an arbitrary subset of V, not necessarily a subspace, just a subset. We define the following set S perp, perpendicular, to be the set of all vectors W and V such that the dot product or inner product or scalar product of W with V is 0 for all vectors V in the set S. Using our scalar product properties 2 and 3, we quickly see that this set, S perp, is indeed a subspace of V. So S perp is called the orthogonal complement or the orthogonal space of S. And again, we note the orthogonal complement of S is a subspace of V, regardless of whether S is or not. Okay? Now next, let's again, do the following. We have our set S is a subset of V. Let U be the subspace of V spanned by S, or generated by S. In other words, let U be the span of S. So U is a subspace of V. It's the subspace of S spanned by the linearly independent vectors in set S. Now, so using the scalar product properties, if a vector W in V, if it's perpendicular to S, then it would necessarily also be perpendicular to U. And you see the proof there using SP2 and SP3 that, if V1 and V2 are in S, and then you look at W inner product with the sum, it distributes, you get 0 plus 0 is 0, and the scalar factors out, you get C0 equals 0. And so if a vector is perpendicular to S, it must be perpendicular to the span of the set S, which I'm calling U. All right? Now, my notes here are more detailed than what the book has here. We're looking next at example 3. Example 3, which is looking at a homogeneous system of linear equations. So let A be an M by N matrix over the scalar field K. Let's consider the homogeneous system of equations AX equal to 0 vector. Now remember, the 0 vector is in Km. Km. Let A sub 1, A sub 2, A sub M be the rows of A. Then AX equals 0 can be thought of as a system of equations, A sub 1 dot X equals 0, A sub 2 dot X equals 0, through A sub M dot X equals 0. That is the ith row of A dot product with the column vector X equal to the scalar 0. Okay? Now, so just for notation, let S be that set that consists of the rows of the matrix A sub 1, A sub 2 through A sub M. Let W be the subspace of Kn spanned by the rows of A. W actually is the row space of A. It is the subspace of Kn spanned by the rows of the matrix A. All right? Now next, let U be the kernel of A. That is, U is the set of all solutions to the homogeneous linear system, AX equal the 0 vector. But the way I have this problem set up now, we can clearly see that the orthogonal complement of W perp, is equal to U. The orthogonal complement of the row space is equal to the solution space. Okay. So now we can go back to chapter 1 where we looked at direct sums and notice now that Kn is the direct sum of W with W perpendicular. And then looking at our dimension theorem, the dimension of Kn equals the dimension of W plus the dimension of W perpendicular. So N is equal to R plus N minus R, and the dimension of W is the rank of the matrix. The rank of the matrix. Okay. Now here's a definition. Let B equal V1, V2 through V sub n be a basis for the vector space V, where the vectors in the basis are mutually perpendicular. That is, the inner product of Vi with Vj is 0 whenever I is not equal to j. They're mutually or pairwise perpendicular. Then B is called an orthogonal basis for V. Orthogonal basis. Okay. Now, the remainder of Chapter 5, Section 1, we're going to restrict our scalar field K to be the real numbers. We'll look at the complex case in the next section and in subsequent sections. So the remainder of the first section is the real case. And we're going to look at what we call the real positive definite case. Now, the property called positive definite could also be labeled as SP5. All right, the real positive definite case. Let V be a real vector space over the real numbers, R, with a scalar product. The scalar product is said to be positive definite if the inner product of V with itself is non-negative, greater or equal to 0 for all vectors V, and actually positive whenever V is not the 0 vector. The dot product on Rn is positive definite. So is the one from example 2 where we had the continuous functions and the scalar product was defined by the definite integral. But now notice we didn't say that the dot product on Kn is positive definite. In particular, if you look at the complex numbers, Cn, it is highly not positive definite. But now, still restricting our attention to the real number case, here are some familiar definitions that you should remember from previous math courses. For any V in V, the norm of V, that is, the length of V, the distance from the 0 vector to V, is the square root of the scalar product of V with itself. And if C is a real number scalar, the norm of CV is the absolute value of C times the norm of V, which you can clearly see here because the norm of CV is the square root of the scalar product of CV with CV. Factor out both C's, you have C squared, and then V with V. Square root of C squared is the absolute value of C times the norm of V. Okay? Next, we define distance between two vectors, V and W, in the following way. D of VW is the norm of V minus W. It's also equal to the norm of W minus V, which is the square root of the inner product of V minus W with V minus W. Now here's a geometric view of perpendicularity. You know, we define two vectors to be perpendicular if their scalar product is equal to 0, right? Or if their dot product is equal to 0. Well, looking at the triangles here, we see a geometric justification for the definition of perpendicularity. Here it is. As you look here at the triangles, the one on the left is scalene, the one on the right is isosceles. We note that the norm of v minus w equals the norm of v plus w. That occurs when what happens? V is perpendicular to w. So as you look at that, these are all non-negative quantities. So that's true if and only if you take the square on both sides. So that's true if and only if v minus w squared equals v plus w squared. And then use the good old binomial expansion. You have v squared minus 2vw plus w squared equal v squared plus 2vw plus w squared. Combine like terms, you have 4 v dot w is 0, which means v dot w is 0. In other words, v and w are perpendicular. So that's our geometric justification for the definition of perpendicularity, meaning that two vectors are perpendicular if their scalar product equals 0. Okay. Now next is just a familiar definition of a unit vector. A unit vector is a vector whose length is 1, whose norm is 1, and if v is not the 0 vector, then if you divide vector v by its norm, then you have a unit vector in the same direction as the vector v. Now next we get to the good old Pythagorean theorem, or as our book calls it, the Pythagoras theorem. C squared equals a squared plus b squared. Okay? All right, so whenever two vectors are perpendicular, v and w are perpendicular, then the norm squared of v plus w equals the norm of v squared plus the norm of w squared. It's just telling us the Pythagorean theorem. The hypotenuse of a right triangle squared is a squared plus c squared equals a squared plus b squared. All right, so look at the proof. It's very straightforward. The norm squared is just the scalar product of v plus w with itself, v plus w. And so we're just using, binomial expansion, multiplying two binomials together by what? The FOIL method. The FOIL method. First, outer, inner, last. The good old FOIL method. So it's the scalar product of v with v plus twice vw plus w with w. So that's the norm of v squared, and then v and w are perpendicular, so their scalar product is 0. So you quickly see that you get the norm v squared plus the square of the norm of w. Then next is the familiar parallelogram law from geometry. Now let me adjust my paper here. At the bottom of my paper, notice my parallelogram. I have my parallelogram drawn, and the 0 vector, or the origin, is at the center of the parallelogram, and emanating from the center are the two vectors v and w with their opposites, negative v and negative w. Connecting their endpoints, we have the parallelogram, where opposite sides are parallel and have equal length. So the parallelogram law tells us that the square of the sums of the sides, v plus w with v minus w, is equal to twice the norm squared of V plus twice the norm squared of W. All right, so just simply apply the definition. V plus W norm squared plus V minus W, the norm squared. You're just using FOIL on each one of those individually. You have norm V squared plus twice VW plus norm W squared plus norm V squared minus 2VW plus norm W squared. So the inner terms cancel out, and you're left with 2 norm V squared plus 2 norm W squared. So that's the parallelogram law. Here, I was looking at the same picture with just making sure I had the symmetries correct. Okay. Now next, we're going to look at what we call the orthogonal projection of a vector V onto or along W. Orthogonal projections. This here is the foundation for what's coming, namely the Gram-Schmidt orthogonalization and orthonormalization process. So when we have two vectors, V and W, emanating from the origin 0 vector, having the same common starting point at the 0 vector. And in my diagram, notice that W is drawn with a longer length than V for the sake of simplicity. Okay. Let W be a given vector in V whose norm is not 0. So it's not the 0 vector. Then for any vector V in V, there exists a unique scalar, real number scalar, C and R, so that V minus CW is perpendicular to W. And so we want to develop a formula for the scalar C here. So if we just set it up this way, by looking at the inner product of V minus CW with W, set it equal to 0 because we want it to be perpendicular. And just use our SP2 and SP3. We have the inner product of VW minus C with WW is 0. Add the second term to the right side and turn it around. So our scalar C is the inner product of V with W divided by the inner product of W with W. So the scalar product of W with W can also be written as the norm squared. And I like to write it as the norm squared sometimes. All right, now next is the famous Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality comes up in all areas, lots and different areas of mathematics. It's theorem 1.1. Theorem 1.1 on page 100 and 101. Cauchy-Schwarz inequality. It says the following. For any two pairs of vectors, V and W in V, it turns out that the absolute value of the scalar product of V with W is less than or equal to the norm of V times the norm of W. Now, this is also true over the complex field as well. But here we're in particular looking at the real case. Now, this is true trivially when W is the zero vector. You just get 0 is less than or equal to 0. And so we can, without loss of generality, we can suppose that W is not the zero vector. Now, referring back to our figure, I labeled it up here as figure 1, our drawing, we note that we have a right triangle, and the two legs of the right triangle are CW and V minus CW, and the hypotenuse is the vector V. So we can apply the good old Pythagorean theorem to it. Right? C squared equals A squared plus B squared to prove the Schwartz inequality. So we have that the norm of V squared is equal to the norm squared of V minus CW plus the norm of CW squared. Now, this means that the norm of CW squared is actually less than or equal to the square of the norm of V if we take out the V minus CW term. So that means that the absolute value of C squared times the norm squared of W is less than or equal to the norm squared of V. Square root both sides. Square root both sides. You have the absolute value of C is less or equal to actually the norm of V divided by the norm of W. I didn't write that out there, but that's exactly what you have. Let me write that out on the side there. Norm V over norm W. I'm sorry it's a bit messy to follow here, and then if you multiply the norm W squared in the denominator from the left side and over to the right side, you'll note that one term cancels out, and you now have proven the Schwartz inequality. So the absolute value of VW is less or equal to norm V times norm W. And this Schwartz inequality is used over and over again in proving theorems, not only in linear algebra, but in other areas of math as well. Then finally, we have the famous triangle inequality. Triangle inequality. Now, the triangle inequality in geometry says the length of the longer side of a triangle is less than or equal to the sum of the sum of the lengths of the other two sides. That's what it says. All right. So if we have the following, V and W are two vectors in V. The triangle inequality says this: the norm of V plus W is always less than or equal to norm of V plus the norm of W. Now, all of these quantities are non-negative, greater or equal to 0, so it suffices to show it for their squares. Show the square of the left side is less or equal to the square of the right side. All right, so let's show that W plus V plus W squared is less than or equal to the norm of V plus the norm of W squared. Well, we're just going to use the good old FOIL method, first outer, inner last. V plus W squared is V squared plus 2VW plus W squared. So that's the norm of V squared plus 2 times v dot w plus the norm of w squared. Now, this next step is using the Cauchy-Schwarz inequality, theorem 1.1, where we can put in here that this is less than or equal to now the norm of v squared plus twice the norm of v times the norm of w plus the norm of w squared. Now the right-hand side now is a perfect square, namely norm of v plus the norm of w, all quantity squared, in parentheses squared. So we have some familiar theorems, the Pythagorean theorem, the triangle inequality, parallelogram law, and so this is the summary of section 5.1. Our homework for this section, homework 9, is on page 103. Exercises 1 and 2. 1 and 2. And that concludes our lecture for section 5.1.